I'd like to thank the organizers. It's really nice to be here, and it's a very stimulating workshop. So I'm going to talk about good metals. Well, let me thank my collaborators. Actually, the data I'm going to present was started on with Shaolin's thesis on S-transform titanate. Alexandre Jaby, who is now in Munich, worked on antimony. Clément Collignon and Willem Richaud were also continuing the work started by Xiao. My younger colleague, Benoît Fouquet, has been actually associated in all this work. So what I'm going to talk about first is really very elementary, old-fashioned physics about what do we know about T-square electrical resistivity. Several speakers here mentioned that if you have a Fermi liquid, you have a T-square resistivity, and it looked like it is the end of the story. I would like to convince you that this is not the case, actually. And then I'm going back to helium-3. Actually, I learned a lot by looking at all literature in helium-3. And of course, if you have questions, please be patient for the third talk. If you want to really contest, because I'm going to make a connection to bad metals, cuprates. There was no talk about this, and well, you will see the connection, how to go from weakly correlated, well-understood Fermi liquids to something as controversial and enigmatic as the strange metallicity of cuprates. So let us begin by this statement. You have a Fermi liquid. This is what you expect at the resistivity, ρ0 plus He squared. Now, the original idea is very simple, proposed by Landau and Pomeranchuk from one side and Baber from the other side of the iron core tail, almost simultaneously. The whole idea is that you are applying Pauli exclusion principle to two colliding electrons. For each of them, you have KBT over EF. So the phase space is going to go like KBT square over EF squared. Now, one important detail as an experimentalist, if you want to see this in copper or gold, it's hopeless. You need either a correlated metal or a dilute metal. But in both cases, it is obvious. So I'm showing all data from several other groups. This is bismuth data by Hartmann, graphite. So these guys are semi-metals, but it is also forgotten. These guys have a mobility of 1 million. It goes out of, Simone just showed the curve of mobility. These guys are as competitive as graphene. Bismuth actually has the highest mobility besides 2D electron gas in one direction is 10 to the power of 8. So these guys are semi-metals, but you can see, as you can see, you can clearly see T-square behavior in graphite, and actually they have been a little forgotten. And now I come to this early data. So the idea of T-square resistivity was proposed in 37, but yes.
So the situation is different topograpically from very dilute metals and things like quantum glutamate, right? In very dilute metal, we have the problem of the small band surface and fast scattering through the lab. Right?
Yeah, you will see. I am going to address all these questions. But my first question is, here, I think in my slides, you will see a lot of experimental numbers. So if anything is contestable about numbers, so these are data. Okay, I would say that if you put a bismuth crystal, this is a kind of your student, you see this square term, and yeah, this has numbers. I'm going to talk about this. Of course, theoretically, you can say, well, you are surprised by some or not by others, but these are. So the first person who actually is Rice, for some reason, actually, he is the initiator of what is now called the Kadowaki-Woods scaling. Rice did it, and there is a reason for that. So this is mostly about history of condensed matter physics. So Rice was, interested in palladium's T-square resistivity, which is large enough to be measured. And then he put these, numbers for several elements. I don't know if you can see it. This is rhenium, this is cobalt, iron, platinum, nickel, and palladium. And he had this nice scaling between the prefactor and gamma square is the Sommerfeld ratio. You see the Sommerfeld coefficient, the T-linear specific heat. And it makes sense because, as I'm going to talk in a minute, you expect both of these guys to scale with density of states. What Kadowaki and Woods did after the discovery of heavy fermions is that actually for heavy fermions, you have a scaling which is different from these weakly correlated systems. This is why actually Kadowaki Woods became much more famous because most people were interested in these strongly correlated systems. Now, one thing that one should keep in mind, but why does it work? You don't need actually, you need condensed. Yes. Yes, yes. But that is not a contest. This is actually means that, you see, this is over 5 orders of magnitude. I'm going to show stuff which is in over 10 orders of magnitude. So, the whole point is that if, as a theorist, you can predict something, even with a factor of 2 or 3, I would be impressed if the scaling works over 5 orders of magnitude. You showed activation. The first thing about the activation is that if it doesn't work over 1 order of magnitude, how can you consider this as an Arrhenius plot? So, these are observations about the very plot. This is logarithmic, but unique. So I'm going to show some logarithmic plots like that. So to understand this, actually, you need just condensed matter physics at the level of Ashcroft and Mermin. The whole idea is that a specific heat in a, let's say, free electron gas scales with EF. For resistivity, we don't know. Actually, the trick is what gives you T-square resistivity. As Antoine said, it is not at all obvious. But, as it was mentioned, we have a scale of resistivity, which is h bar over E2. Then we know that it should scale with EF squared. So the only thing which is remaining is some phenomenological length scale that we don't know what is it, and it should be material dependent. Now, you would expect this scaling to work only if you have 1 electron, roughly 1 electron per formula unit, which is the case for most metals, but not all of them. When n is smaller than 1, you cannot see this work. And actually, if you look at, this is actually the scaling. So here, I am showing now the log-log scale. You see that Rice scaling was here. It works very well, but he forgot, or he did not include bismuth, graphite, and antimony. Well, at least bismuth was measured at that time. So for somehow it was but as if you put now the scaling as A over EF, you see that these guys also work. And in the case of fermions, 2 examples that I know is cerium, nickel, tin, and uranium retained to silicon 2. Again, they don't work on normal Kadowaki-Woods plot. So the message is that if you want to know the magnitude of A, it suffices to know within an accuracy of 2 the magnitude of your Fermi energy, and you can guess the level of what gives you the magnitude of A. And the reason I became interested in this physics is again connected to what Antoine said, is that we found that actually in strontium titanite, you can have T-square resistivity. You can change the carrier density by a factor of 200 here, actually more. And our data joins actually what was measured by van der Marel and by Tokura. And you see that over 4 orders of magnitude, basically this A is varying smoothly. And the question is, how come that this T-square resistivity persists when what we believe to know about the mechanism of this T-square resistivity is absent? Basically, here we have a single component, small Fermi surface, and this is not just from one structural calculations. This is also confirmed by quantum oscillations, which have quantified, the size of the Fermi surface and the mass of electrons. Okay, strontium titanite. Yes. Yes.
So the value of that here,
is here. This. No, sorry. Umklapp is here. Here you have several bands, but you can immediately see umklapp maybe at 1020. Yes.
So if I look at the stage that
no, but the mass changes. You see, you have 3 bands. The dispersion is different. So again, excuse me. No, very high doping. So we have a Lipschitz transition here, another Lipschitz transition here, but the Van Hoff singularity happens at much higher doping. Even at 10 here, I have just 1% of, doping. Yes, exactly. This is a Lipschitz transition. Yeah. Yeah. So the Lipschitz transition is here. Yes. Yes. And you see that there is a kind of kink. Yes. So Strontium titanate has a very strange, very interesting ground state. You have soft phonons, and actually the whole physics is not electron-electron scattering, because we cannot understand why T-square resistivity actually goes beyond the degeneracy temperature. Now, the thing is that it's not alone. So this is a second system discovered in 2020. Well, these data comes from my former student Xiaolin, who actually showed that this is actually not, the Fermi surface is very simple. It's at the gamma point. Again, band structure works. There is fermiology, and you have, again, a T-square resistivity. And no, the problem is we don't know why T-square resistivity in these cases work, because the two cases for T-square resistivity, the first was covered by Bubble, that you have a bottleneck for losing momentum to the thermal bath. If you have two types of electrons, one of them more tightly connected to the phonons. The second process that you can imagine in any case is if your Fermi surface is large enough to have umplap. If your Fermi surface is large enough, electron-electron scattering normally loses some fraction to the fraction of collisions which are umklap will give rise to the resistivity that you are seeing. It looks like in any case, any momentum exchange between electrons somehow is taxed by the lattice thermal mass. And now I am showing, a phasor again. This is a logarithmic. There is not one line. Actually, you can distinguish between the Kadowaki-Woods line and the Rice line. There is a difference of a factor of 25. The whole point is that the order of magnitude over 4 orders of magnitude of Fermi energy or 8 orders of magnitude of A, you can more or less give an idea of what you expect. Of course, this is not universal. You have, when you have a difference of factor of 20, you would say that the cross section is not the same, and microscopic details should matter. No, but I would say there are two questions. One of these is that if you have several mechanisms for generating this T-square resistivity, how come that knowing the Fermi energy gives you this predictive power, again, between a factor of 10? And why does it persist even when you don't have umklap, which is what you expect to give it rise to this? Now, I want to switch gears, because this is my expertise, is thermal transport. Now, thermal transport measurements are more difficult, but there have been data. So I am showing again two curves. One is on tungsten, a weakly correlated system, and one is cerium, rhodium, indium 5, a strongly correlated system. So as you know, there is something called the Wiedemann-Franz law, which we take very seriously. If you don't recover the Wiedemann-Franz at 0 temperature, most probably your experiment is wrong. This is actually the lesson of the last 30 years, where several violations of the Wiedemann-Franz law have been reported and then retracted. But at finite temperature, actually, you can have a difference, and you see a difference. The resistivity, the thermal resistivity is larger than electrical resistivity, but by a factor which is always of the less than an order of magnitude. So normally, there is a good understanding why thermal resistivity should be larger than electrical resistivity. The simple answer is that in one case, you are interested in momentum flow, so it's a vector quantity, so small angle scattering matters less. When you are measuring thermal resistivity, actually it's simpler, it's a scalar at the energy, so you are not, you can imagine that all scattering events matter as much. The reason I'm mentioning T-square resistivity is because now we can make another connection with the original Fermi liquid. So you see, helium-3 was a subject of intense discussion back in 1980s. And what was known is that actually, this is where the whole story of T-square began. You have the phase space of fermion-fermion scattering, and it is T-2. And people were amazed by the fact that the viscosity of helium-3 becomes as much as olive oil at 40 degrees Celsius, but at 3 millikelvin, just before the superfluid transition. And all this is driven by fermion-fermion scattering. And people have measured, so this is the most complete work on thermal conductivity of normal liquid helium-3. And what people were talking about is that thermal conductivity is going to vary of 1/T. For reasons that I don't know, there is no trace of anybody comparing this data with what happens in metals. So in metals, we call it thermal resistivity. You see it's WT over And it is the inverse of kappa over T because people are mostly interested in resistivity. So if you want to compare your thermal conductivity data with your resistivity data, you don't take just the thermal conductivity, but thermal conductivity divided by temperature. So if you say that my thermal conductivity is proportional to 1 over T, it's exactly equivalent to saying that your thermal resistivity defined this way is T squared. And now I have replotted Ray-Wall's data. And it is interesting because you see, basically what he's saying is a T square thermal resistivity, which is has a slope, which is small here, where you are uncorrelated. So this is the phase diagram of helium-3. Antoine mentioned it briefly at the end of his talk. This is the Pomeranchuk, anomaly. So you have a liquid. When you compress it, it becomes a solid. Now, here is the context in which we became interested. Yes, yes. Yes. It's impossible.
Doesn't have a conservation, but particle transport, the current produced with the electronian conductivity is infinite or resistivity is 0. So for thermal conductivity, it's not a problem. There are only flaps.
I know. This is what.
Not only fraction plays a role, but of course for transport.
No, but yes, but you are asking, exactly in helium-3, there is no such thing that the particles are not charged. So we are talking now about energy diffusivity, and the only bridge between the two is the Widman-Franz law. This is why at the end we come back at the end to what you prefer. What I am saying may have no relevance for electrical resistivity of metals. You see, but it has of course relevance for thermal resistivity of metals. Okay, so you can then say that, okay, what you say is nice, but it doesn't give any clue about the origin of T-square electrical resistivity in metals. But in that case, you would expect a gross violation of the Widman-Franz law at finite temperature. So I get your point, but now I'm just talking about energy transport. Okay.
But the message is supposed to be that the Landau parameter changes as I go to the.
Exactly. I am going to talk about that. Actually, this is the heart of my story. Yes. Okay. So we are talking about this actually. Landau parameters in a Fermi liquid in which translational symmetry, is perfect. There is no discrete. You have basically no lattice, and of course you cannot measure electrical resistance. So the reason we became interested in this is because so tungsten diphosphide discovered a few years ago. It's a very interesting system. It has a high mobility, and the first, study on on Fib, nanometric samples give this value for L over L naught, which did not respect the Widman-Franz law. So we did it again on crystals, and what we found out, okay, Widman-Franz law is respected at when you go to very small temperatures, but indeed a strong deviation, maybe a record deviation from this value can be seen in this region. And for that, we could, actually find the T-square term and the T5 term in resistivity. Actually, for phonons, resistivity is not T cube, T5, it is T cube in Bloch-Brunneisen picture, again, because you don't have this small angle, scattering, which gives you an additional T2. It's just the population of phonons. You see, thermal resistivity is even simpler. So, yes?
So if I go to T2,
Mm-hmm.
the fact that when you John in elastic gap, you get a different sort of behavior, depends on if it will do, it's not the standard line. It's not surprising itself, right?
It's T-square. My point is that even here you have a T-square term, and you can quantify, you can see it actually. This is a T-square term, you have a T-square term. Yes, and here is the table, you can see here. So this is a list of everything. So people have measured, and the whole point is that how large can be this difference between the B term in thermal resistivity and the A term in electrical resistivity. The record is not actually ours, it is in tungsten. And so theory says that. So there is an old paper by Herring, he said that actually this ratio should be of the order of 2. He has an argument that even in complicated Fermi surfaces data, actually, Maslow and his collaborators showed that in semi-metals, actually this number can be arbitrarily large. But in both cases, it should not depend on sample size. If you forget about normal scattering, if you are only interested in umlaut scattering, you see, we have a difference between thermal resistivity and electrical resistivity. So the traditional way of understanding this, without invoking any hydrodynamics, is that the reason you have more thermal resistivity and electrical resistivity is that you have vertical and horizontal events. This is what is in Zeiman, let's say. But if you look at helium-3, you have a thermal resistivity, which doesn't need any umlaut. This should be also valid for metals. So you have a difference between momentum relaxing and momentum conserving collisions. So in that case, B over A should be partially because of the fact that normal collisions affect thermal transport, but not electrical transport. And how can we be sure that, how can we distinguish between these two? You can look at the solid with ballistic electronic transport and look at the ratio. And this is what we did in antimony. So this is a recent work. So you see, antimony is the same metal, okay? You can see T-square resistivity. But what is interesting is that these are millimetric samples. So I change the size of the sample, and I see that at high temperature, nothing happens to resistivity. The resistivity is very small. So you see, we are talking about several tens of nano-ohm centimeter. The mean free path is of the order, but less than the sample size. But you see that if you cut your sample, actually you decrease your conductivity, you decrease the mean free path of your carriers. And the same thing when you do the thermal transport measurement. You see that we have a lot of noise because thermal conductivity is so large that at these temperatures, it is about measuring temperature gradients which are of the order of microkelvin. So this is why we have a noise, but the Wiedemann-Franz law is conserved. This one, we didn't go to low temperature. So what happens here? Basically, there's a sample size in the sense that the higher the size of the larger the size of the sample, this ratio of B over A increases. So this is up to here, it is not surprising. We can say that a substantial fraction of electron-electronic scattering conserve momentum. And this is what gives you actually, we can have this was predicted in the context of graphene by Vignal and Principi, who actually suggested that, well, if you don't have any umlaut and you have just normal scattering between electrons, then you can see a violation of the Wiedemann-Franz law at finite temperature, which is scaled with your impurity, with your mean free path of your electrons. And just to say that, you see, I see a difference in violation of the Wiedemann-Franz law, but it doesn't matter on a logarithmic scale. The value of antimony, the T-square term, which is different by a factor of 2 for thermal and electrical resistivity, on a log scale, it is very much comparable to some universal plot for semi-metals. The main message up to here is that you cannot take this prefactor more seriously and ask yourself, what does it tell you? Let's come back to helium-3. Why in helium-3 we have a T-square? Of course, there is a pioneer paper by Abrikosov about how to calculate these Fermi liquid coefficients, which is, even in this case of helium-3, is very involved. But the main ingredients is easy to grasp just by discussion of resistivity, the diffusivity. If you have energy diffusivity or momentum diffusivity, which is nothing else than viscosity, both are going to vary as 1 over T squared. Why, in the case of scattering time, this is what is going to run the show. Velocity is basically Fermi velocity, doesn't change with temperature. Now, since your specific heat is proportional to T, thermal conductivity would be inverse of temperature, and your thermal resistivity, in the language of, again, a metal physicist, is T squared. So what you are measuring basically is something which is going to bring you back to the scattering time between 2 fermions. And actually, this has been done by people in community of heavy fermion, in helium-3. The specific heat increases with pressure. So you see, you increase the correlations, and you end up by solidifying your system. And kappa multiplied by temperature inverse, this is actually the slope of T-square resistivity, if you wish, also increases correlation. So, and theory works very well. This is Fermi liquid theory by Diane Pettit. So the agreement between theory and experiment is really remarkable. And you see, there is no non-Fermi liquid regime. So it is a Fermi liquid, at some point, stops, it becomes a solid here. Well, first remark, if I put helium-3 data, so now I'm not just putting one data, I'm putting all the variation of helium-3. You see, gamma has been measured, and also B is nothing else than kappa T -1 with some fundamental constants. So there's a cross-section here. We see that actually we have a very nice, continuity. It's a common thread between tungsten, which is weakly correlated, to cerium, cobalt, indium-5, to helium-3. Nobody had done it before. So what does this imply? And so coming back to strontium titanate, I just put now helium-3. So this is thermal conductivity for helium-3, and this is electrical conductivity for strontium titanate. For strontium titanate, it's hard for us to measure electronic thermal conductivity because you have a lot of phonons. But for me, it is convincing that the physics should not be fundamentally different. But of course, this is a matter of this brings me to something which may interest you more, some bad metal physics. So we are all, yes. Yes.
So there is also a very interesting set of experiments that are developing about helium-3 as well on the graphite, where the range of the Landau tungsten is way bigger than the bird. So I don't know in terms of measurement there, but perhaps yes, and mostly only those experiments.
Yeah, but this experiment, just say this is a very, very, very so even in bulk helium, you see, so okay, I should show the data. So it is between 20 milli-K and 8 milli-K, so not in the superfluid phase. So this experiment is already a tour de force. So I understand that putting 2D helium-3 on graphite is an interesting system, but I'm not sure that you can do this experiment, thermal conductivity, maybe a specific heat. So it never becomes a solid. You see, one of the questions is that, the reason I want to stay in this situation is that we have a good understanding. These are Landau parameters which are increased, and at some point the system solidify. Okay, so even in the 3D case, I'm going to ask these questions now. Okay, so let's come back to cuprates. So what do we know? We know that there are a lot of lines we don't understand, but there is a Fermi liquid regime. And there is a T-square resistivity here. Actually, it has been studied very carefully by my friend Nigel Hussey. So you see, here is LSCO 33%, and here is LSCO 70%. Here you can see that resistivity is linear in temperature. Here it is T-square. And actually, so what Nigel did is that you can do different type of heatings. What you find is that, so these are the symbols, the circle and the square, are different ways of heating. Either you add resistivities in a two-channel model or you add conductivities. See that there's some difference, but it doesn't change that much. You have a T-square resistivity which maybe diminishes, but it is already there. But it is alone when you get rid of superconductivity. So the interesting observation or puzzle is that how come that we have a good Fermi liquid here at 33%, and then when you go to the superconductor, whatever you do, you can never fit your data with the T-square behavior. You have something more. And then at optimal doping, it is almost purely linear. So this has been the puzzle for the last few decades. And I would like to mention that actually I was involved in, and Hide also in this experiment. We had difficulty publishing this because we found T-square behavior. So if you have, this is not superconducting, at 33%, TC is 0. And at that time, we were also intrigued by the fact that actually this guy is out of this Kadowaki-Woods scaling. But at that time, we didn't take Kadowaki-Woods scaling very seriously. It's an order of magnitude. As Thierry said, it's just a log-log scale. Now let's look at it a little more carefully. Actually, as you know, in these perovskites, metallicity is rare. So I have taken 4 exceptions. Strontium ruthenate, this 2-layer and the single-layer one. This is actually a strontium titanate doped so much, 95%, to not be a Mott insulator, to not be a band insulator, and the Fermi surface as large as the beryllium zone. And this is the strontium vanadate. And you can see that actually this guy has some A term, which is much larger than what you expect. So in our 2015 paper, actually, we had this point about LSCO, which doesn't match. You know, this is the heavy fermion line, this is the transition metal line, this is Kadowaki-Woods line, this is the Rice line, if you wish. And almost everything is between this range. So this guy seems to be strange. So it's a Fermi liquid, TC is 0, but now it is giving us a clue. This guy is ready to become a strange metal. How come? So here I'm an experimentalist, you know, who am I to give any explanation of this? I make observations. As far as I understand, you have 2 time scales. The one is if you have a non-interacting set of fermions, of course, you have a very natural time scale, which is h bar over EF, which is basically the time scale for permutation of 2 fermions in the Fermi-Dirac distribution. Now, if you have an interaction time, which are called tau FF, actually it grows with KBT over EF squared. This is also a time, but normalized by the disponibility of your phase space. And now if you take the ratio of these 2, you have a dimensionless number. And actually this number is accessible to experiment, both in helium-3 and in cuprates. The question is, how large can these dimensional numbers begin, which is intimately linked to Landau parameters of your Fermi liquid. The more correlated you have, the larger should be this zeta. But it means that the larger your Landau parameters are become, the higher is the collision rate between your fermions compared to the time necessary to respect the Fermi-Dirac statistics rule of permutation. Now, you can play this game. So helium-3 at p equals 0. So in helium-3, this is completely unambiguous. You know, people have tabulated all this, Rayval in particular. It is in the book by Volhard and Wolfle. So these are actually textbook numbers. You can have a zeta which is as large as 35, and at solidification, it becomes as large as 60. Now, in LSCO, this number is very large. I'm going to come back to it in a moment. But, you know, much larger than just the mass enhancement is suggested. Mass enhancement is just 5 compared to the electron mass. For the helium-3, I'm giving the mass enhancement compared to the mass of 3 nucleons. UPT3, which has much higher mass enhancement, the problem is that if you want to calculate this zeta, we should circumvent the fact that it has 5 different bands with different masses. This is why, you know, the masses are different. So you have different Fermi energies. But I take just the specific heat and take an average value of carrier density, gives you this, and you see that zeta is actually much smaller. So it is not true that mass enhancement is what is governing this guy. And actually we saw it because Kadowaki-Woods doesn't work with this guy. Same is true for strontium ruthenate. This is little easier than UPT3, but still has 3 different bands with different masses. Now I have also put this weakly correlated system. You see that here actually zeta is below 1. So the whole question is, if you want to look for a place where strange metallicity is born, up to now people begin with, you know, the Mott insulator and say, okay, how a doped Mott insulator can become strange. I begin with a Fermi surface, and the question is, can this number become as large as you want? So, of course, helium-3 was, you know, I don't know if you remember when Laughlin at one point said that there is no such thing as a Mott insulator. Philip Anderson said that actually the best example of a Mott insulator is helium-3. It is a system in which actually M star over M3 is increasing, but you see it doesn't diverge. It is large and suddenly it solidifies. The Fermi energy goes down, which is a combination of M star and the Fermi wave vector. And so these are the numbers given by Grayval. You see that there is a disagreement between Grayval and Whitley, but it is, well, about 30%. So I took Grayval's number. you can take Whitley's number, then the whole stuff will change by 30%. Now, in the case of lanthanum 1.67, strontium 0.33, copper, oxygen 4, actually, the mystery is much less because the Fermi surface is as simple as that. It's an electron-doped Fermi surface. What is special about this Fermi surface is that the Fermi velocity has a strong anisotropy. So if you take the value of A, the T-square resistivity, you can use the root formula. So A is the prefactor of resistivity. Now I'm assuming that it is very much similar to helium-3. So from that, I just calculate the tau times T squared. The index rho means it comes from resistivity and not thermal conductivity. Nobody has measured the T squared thermal resistivity there. And what is amazing is that it completely could be a coincidence. But this number at solidification for helium-3 is of the order of 60. And for this guy, actually, you have an angular variation for nodal quasi-particles, which have a higher, longer mean free path. The scattering time is shorter, and this zeta value is attained, something of the maximum. So this brings us to some speculation. Up to here, what I told you is just, observations. You can agree, or I can defend what are the observation bases. From here is a matter of what happens to nodal quasi-particles. In helium-3, we know what happens. It solidifies. In cuprates, of course, I don't know. I don't think it is. But the question, which is interesting for you theorists, is what happens to Landau parameters at the Mott transition. So what Wohlhard wrote in 1980 discussing helium-3, because it's the best example of a Fermi liquid in which you just put pressure, at some point it becomes a correlated insulator. The standard answer has been that the Mott transition, the Landau parameters diverge, which to me it seems unphysical in the sense that you should have a cutoff somewhere coming from the insulator side. So Luca Medici, my colleague, told me that there are models of K-dependent Mott transition, which may circumvent this kind of behavior. And now let's imagine that this happens. Nodal quasi-particles, because of this cutoff, are excluded from the Fermi sea. Then there is an easy way, I would argue, to explain linear T resistivity. Actually, this idea has been already proposed by Musatov, Bragg, and Hartnoll, who's for strontium glutamate. In that case, actually, the story is that you have a T-linear resistivity because you have classical electrons and you have quantum electrons. How can you have classical electrons in this system? It has a complicated Fermi surface. You have big Fermi surfaces and small Fermi surfaces, and it is just necessary to imagine that what gives rise to this T-linear resistivity is scattering between one electron which is degenerate and another which is not degenerate. In that case, you are going to apply the Pauli exclusion principle to one electron and not to both of them. Of course, you cannot use this scenario for cuprates because you have a single Fermi surface. But the road to strange metallicity inspired by this is complete speculation, would be that actually nodal quasi-particles are somehow excluded from the Fermi surface, whatever that means, and this gives rise to the T-linear resistivity. So, okay, I summarize my talk. I think there is you just put the numbers, there is a connection between the amplitude of T-square resistivity in metals and in helium-3. So here I should put maybe thermal resistivity in metals, but then the thermal resistivity of metals and electrical resistivity of them are connected by Widman-Franz law. This will have some implications for the two puzzles. Why does T-square resistivity persist without umklapp? And why its prefactor can be this, knowing just the Fermi energy? And now, the third observation is that actually there is a dimensionless amplitude of T-square resistivity. And if you just look at the topology of the Fermi surface in heavily doped LSCO, you would expect that if there is a ceiling, this is completely a speculation, there is no justification for it, this subset of carriers are going to meet it first before the others. Thank you for your attention.